Hello, my name is Silas Rodriguez, and I'm a computer engineering student at Texas Tech University. And today I'll be demonstrating a 4-bit input circuit using a OR and a NOT gate. With a quick glimpse at my workstation, you can see a few extra tools and wires that come in handy when developing circuits on a breadboard and testing them. A pin, which is very helpful for the dip switch to flick on and off inputs. They default to on, and I'll get into that here in a moment. And I have a Raspberry Pi, which is plugged into a wall outlet with a 9-volt power supply, which this Raspberry Pi could in the future be programmed, but it is not, however, serving any other purpose besides connecting to the power module, which, if you can see here, is providing 5 volts of power to each side of the breadboard circuit. Oh, and also I have a shame jar for all the LEDs in circuits that I blow or break. For now, let's go ahead and allow the Raspberry Pi to power our breadboard circuits. As you can see, 3 LEDs come on along with our final output LED, and one is off. On screen you'll see a legend that corresponds to the outputs that are being viewed via the LED color lights. We have green, blue, yellow, white, and red. Before continuing on and demonstrating the truth table for this circuit, I would like to break down sort of the components of this circuit, and it's not really easy for me to record one-handed and point at the same time, so please bear with me here. So, first of all, we have the 5-volt power supply from the power module that connects accordingly to the ground and our high, or as others call it, low and high. The resistors provide power to the dip switch, and as well as correspond to their bit counterparts that go into the circuits, which is very difficult to see through this jumble mess of wires. As I apologize, I really cannot fix this, but I did make it, however, easier to view with the LEDs. As the last bit of aside, the black chips you see here are integrated circuits with a quad 2-input OR gates, a quad 2-input AND gates, and a NOT gate, or inverter gates. With this circuit, as power, which is transmitted through the resistors here, reaches to these cords, they by default return a 1 to the integrated circuit that they are connected to. Whenever the dip switch is flicked forward, however, the current will flow to the path of least resistance into a ground, which means that these would return a 0 into their integrated circuit. By doing this, we also ground the inputs so that the LEDs do not stay on when they are not intended to, meaning we have a more stable circuit. We will begin testing values from the truth table in order to verify that the circuit is indeed built correctly. I will be testing all 16 values from the truth table, starting from setting D is equal to 0. As I mentioned before, the circuit starts with all inputs defaulted to 1. Feel free to speed up the video, as this will take some time, and all I will be doing is switching the circuit's switches in order to test different values of A, B, C, and D. The circuit replicated the truth table. Therefore, we've also successfully completed the circuit that is on screen now. Using this, we can determine that the final output bulb will only return true and therefore light if the inverter bulb, the yellow bulb, was lit, or if the B and C bulb, which the white bulb, was lit. If either of these were lit, the output bulb was lit, and if both were dim, then the output bulb would also be dim. This concludes the first hardware project for ECE 2372 at Texas Tech. Wreck 'em.